Hello, Algebra 2. Today we're going to talk about Ingenuity Section 8-3, which is right triangle trigonometry. We have two objectives for this section. The first is to use the Pythagorean theorem and the trig functions and their inverses to solve right triangles. The second is to use special right triangle relationships to solve right triangles. So let's look at our first problem here. We've got a right triangle with legs of 10.1 and 12.2 units. So we know we've got a right triangle. When we talk about the legs, that means the sides that are not the hypotenuse. And one of them is 10.1 units long and one of them is 12.2 units long. And it asks, what is the length of the hypotenuse? So to do this, we're going to use Pythagorean theorem. Pythagorean theorem states that the leg squared plus the other leg squared equals the hypotenuse squared. So this will be 12.2 squared plus 10.1 squared equals h squared, the hypotenuse. You'll hear it a lot of times as a squared plus b squared equals c squared, but it's also leg squared plus leg squared equals hypotenuse squared. So I'm going to do a little bit of calculator work so that I know what these squares are. Let's see here, 12.2 squared is 148.84. 10.1 squared is 102.1. Oh no, not 0.1, 0.01 equals h squared. So let's add those two numbers together. 102.01 plus 148.84 is 250.85 equals h squared. And since we're talking about a length, we're only going to take the positive square root of both sides. And so I need the positive square root of this thing, 250.85, which is approximately, so h is approximately 15.84 units long. And that's how you apply the Pythagorean theorem. I'll give you a moment to look at that. And let's move on to the next question. Determine the value of x. So again, we've got a right triangle, and we want to know the hypotenuse. And now we're being given some information in sort of disguised forms here. From geometry, you should remember that if you mark two sides like that, it means that the two sides are congruent, that is, they have equivalent measures. So if this one's 6, so is the other one. So I should be able to just apply the Pythagorean theorem again and say 6 squared plus 6 squared equals x squared, because x is now my hypotenuse. And 6 squared is 36, so 36 plus 36 equals x squared. 36 and 36 is 72. So 72 equals x squared, and then I'll have to take the positive square root of both sides, only the positive square root, because I'm not interested in the negative square root, because I'm dealing with a length, right? So I get that x is approximately 8.49 units long, or x is exactly the square root of 72 units long. So either of those answers might be requested. I'll pause for a moment and give you a chance to look at that. And let's move on to the next question. All right, so what can you conclude about the triangle? So they give us all the lengths in this triangle. We might want to note that it's a right triangle. That might be important. If it's a right triangle, trigonometry applies. However, I want to point out something. Let me reproduce this triangle. I'll make it a little bit smaller. But so I've got a 4 here, oops, a 4 here, and an 8 here. Now, the thing that I want to point out is that if I put a second right triangle, if I sort of flip that one over, and it was 4 here and 8 here, then I would be looking at a regular right triangle, that is 8, 8, and 8. Okay? And what's interesting about this is that this helps to tell me a whole bunch of things about the triangle. For instance, let me draw it one more time. So we've got 4 times square root of 3, we've got 8, and we've got 4. If I consider this angle, let me call that angle theta. Again, this is the Greek letter theta. And let's say I have this angle, and we'll call this angle phi, the Greek letter phi there. And usually it's very traditional to use Greek letters for the measurements of angles. That's typically how it's done. Okay? So if I go back to thinking about this, which converted to this, in a regular right triangle where all the sides are the same and all the angles are the same, all of these angles are 60 degrees, meaning that angle phi let me try that again. Angle phi has to be 60 degrees. So if this one's 60 degrees and this one's 90 degrees, then what do I know about theta? Well, I know that if I add all 3 of them together, I get 180 degrees, right? So I've got a 90 degree one, a 60 degree one, and then angle theta, and it has to add up to 180 degrees. 90 and 60 is 150 plus theta equals 180. And then if I subtract 150 degrees from both sides, I get that angle theta has to equal 30 degrees. Which should also make sense from this picture, because the big angle here is 60, but this line cuts it in half, bisects it, because it bisects that segment, and so each half has to be 30 degrees, half of 60. Okay, so we know a whole bunch of things there. You could also talk about the trig functions here. I can't remember whether this problem wants you to talk about the trig functions yet, but it's something that we could definitely do. You could say, for example, that the sine of angle theta is the opposite over the hypotenuse, so is 4 over 8, which you could reduce to 1/2. You could say that the cosine of theta is the adjacent over the hypotenuse, which then 4 over 8 still reduces to 1 over 2, and so the cosine of theta is 1 times the square root of 3, which is just square root of 3 over 2. And you could say the tangent of theta, which equals the opposite over the adjacent, is 4 over 4 times square root of 3, which 4 over 4 is 1, so you could call that 1 over the square root of 3, which you could rationalize and do all sorts of other things with. If you multiply it by square root of 3 over square root of 3, you get the square root of 3 over 3. So those are a lot of the things that you could conclude about this triangle. You know all the angles, you know a lot about the trig functions, that sort of thing. All right, I'll let you take a look at that, sort of take that in before we move on to the next one. All right, moving on to the next problem. Let's find the sine, cosine, and tangent of angles D and E. So here's D, here's E. And so, again, the sine of any angle is the opposite side over the hypotenuse. So, for the sine of angle D here, D, the opposite is start at the angle and go through the triangle until you hit a side, and that is the opposite side. So this side is the opposite side. So the opposite side here is 8, and the hypotenuse is over square root of 185, and you might put that into a calculator, you might not, whatever. Right? The cosine of angle D is the cosine of any angle is the adjacent side over the hypotenuse. The adjacent side is the side that is not the opposite and not the hypotenuse. It's the side that is not the hypotenuse that is attached to the angle. Okay, so for angle D, this side is the adjacent side. So then we get 11 over the square root of 185. Okay, and then the tangent of angle D. Tangent is tangent of any angle is the opposite over the adjacent side. So this would be 8 over 11. So there's for D, and then we can do the same thing for E, right? The sine of E, of angle E, is the opposite, which would be 11 over a square root of 185. The cosine of angle E is the adjacent, which would be 8 over the hypotenuse, which is square root of 185. And the tangent of angle E is the opposite, which is 11 over the adjacent, which is 8. Notice some similarities here. The sine of D and the cosine of E are the same answer. The sine of E and the cosine of D are the same answer. And the two tangents are reciprocals of each other. That is not a coincidence. That is how it works in every right triangle. I'll give you a moment to look at that. All right, let's move on to our next problem. Find the correct values for the variables that make the cosine of h equal x over y true. Okay, so then find the length of segment GH. So the cosine of h equals the adjacent side over the hypotenuse. So we find h, and the adjacent side is that side. We have the hypotenuse. The hypotenuse is 80. So the cosine of angle H is equal to whatever the adjacent is over the hypotenuse, which is 80. Now, I can figure out what the measure of angle H is, right? Because 33 degrees plus 90 degrees, that's this one here, plus whatever angle H is, equals 180 degrees. And so that would be 123 plus H equals 180. Subtract 123 degrees from both sides, and I get H to be, what's 180 minus 23? That's like 57, right? Yeah, 57. So what this comes down to is that the cosine of 57 degrees is equal to the adjacent side over 80, and I can solve this like a like an algebra problem. Okay, so if I just multiply by 80 on both sides, then I'll have A on that side, and then I need my scientific calculator, and I need to make sure that my calculator, no matter what calculator you're using, that it is in degrees instead of radians. Usually scientific calculators, you have to specify radians. Usually in graphing calculators, you have to change to degrees, so be careful about that. So I want to do the cosine of 57 degrees times 80. So that's 43.57 approximately. And this will be in whatever units they are, right? And so so we found everything. We didn't really, I guess, do this except for we did replace the H, we did replace the Y. The X we just renamed as A. We could have renamed it GH. But either way, so we got that length, which is this length here. I'll give you a moment to look at that. All right, let's move on to our next problem. How would you find the measure of angle B? The measure of angle B. Well, if we start from angle B, let me redraw this. If I start from angle B and I'm given that length and that length, to get there I have to go through, so that is 8 is the opposite side, and square root of 89 is opposite the right angle, so it's the hypotenuse side. So I've got opposite and I've got hypotenuse, and so this is sine, right? And so the sine of B equals opposite over hypotenuse. So the sine of B equals 8 over the square root of 89. So I'm just filling in things that I know, okay? Now, the trick to a problem like this is to then take the inverse of this. So I'm going to take the inverse sine of the sine of b equals the inverse sine of 8 over the square root of 89. And you might want to do a problem like that on desmos.com, because it's a little bit easier, it's a little bit friendlier on there to do it like that. You choose the graphing calculator, and you can just use it as a calculator. Okay. And the reason I like doing it this way is because you can put square roots in directly, things like that. So what I get is that the inverse sine cancels the sine and gives you b, and that equals, when I put it into Desmos, I got approximately, this is approximately 1.01, and that is in radians. And so I get 1.01 radians. I could also get this in degrees if I go back and change from radians to degrees, and then I get approximately 57.99 degrees. And you might have to be careful and make sure of what you're looking at there. Okay? So I'll give you a moment to look at that. And let's move on to our last question. So in this one, we've got a 9.5-foot pole casting a shadow. So here's the pole. Sun's up here somewhere. Casting this, or casting this shadow. And this would be the angle, especially if we look at angle L, that would be the measure of elevation of the sun. Like if you're standing on the ground, how far do you have to tilt up your head? At what angle do you have to tilt up your head to look directly at the sun? Remember, don't look directly at the sun, kids. And we'll see what we can do. Okay, so I've got 9.5 feet here. I've got 29 feet there. And I want to know the angle of elevation of the sun, which is angle L. Okay, this angle right there. So if I look at how to get there, I've got the opposite side that I know, and I've got the adjacent side that I know. So I've got opposite and I've got adjacent, and if you look back, that is the tangent function. Okay? So I know that the tangent of angle L is equal to the opposite side, which is 9.5, over the adjacent side, which is 29. And I can just use that inverse function again, and this time it does actually ask for it in radians, so I'll be able to just straight use radians. I want to use the inverse tangent of the tangent of L. That'll just get me L by itself equals the inverse tangent of 9.5 over 29. So that gives me L equals, and it'll be approximately, and then I'm going to go to Desmos again, and we'll put in this one. The inverse tangent of 9.5 over 29. And we want this in radians, so I got to make sure that I'm in radians. And that is approximately 0.32 radians. So that gives me everything that I need. And there's the measure of my angle. Well, I hope this has been informative. Thank you so much, everybody. I'll see you next time.